My name is Mukhtar Ahmad and I am a PhD student at LUMS. I am going to present Neutrino, a new cellular control plane designed for 5G and future generations of the cellular networks. This is a joint work with my advisors Zafar Qazi, Zartash Uzmi, and a group of fantastic undergrad and grad students at LUMS. Our goal in designing Neutrino is to support low delay budget applications such as driverless cars, AR/VR, and remote surgery. These applications require high reliability and low latency in the order of few milliseconds. A key bottleneck in achieving these goals is cellular control plane. Control plane operations such as service establishment and handover contributes into the application latencies. A study conducted across the 4 major US carriers shows that service establishment happens every 106 seconds and on average, and it adds 168 milliseconds into the application latency. Handover occurs every 70 seconds in the walking scenario, and it contributes 24 milliseconds into the application latency. Wide area roaming is less frequent than the handover, but its contribution to the latency is significant. It adds 900 milliseconds into the application latency. And if failure happened during a wide area roaming, the average delay is 3 seconds. Now the question is how control plane latencies can be reduced. Currently, the control planes are deployed in remote data centers, which results into the control path inflation. Bringing the control plane closer to the user improves the control path inflation problem, but it brings some other challenges. We aim to design a cellular control plane which addresses all the challenges in an edge-based cellular control plane plus some other general challenges. Now I will talk about some specific challenges in the cellular networks. The first challenge is the user state inconsistency due to the control plane failure. In this example scenario, I will illustrate how user state inconsistency is possible in the cellular control planes. We have 2 control plane functions, the primary and the backup. The primary actively serves the users while the backup is having a copy of the user state. When a user moves from tracking area 1 to tracking area 2, it sends location update message to the primary CPF, and the primary updates the user location to tracking area 2. If the primary fails, the backup will become the new primary, but instead of tracking area 2, it is having tracking area 1 as a user location. On data session request for the user, the new primary will send paging message to the outdated user's location. Therefore, the data session will not be successful. In summary, user state inconsistency is possible in the cellular networks, which can cause long delays in the data access. The second challenge is the frequent control plane handovers, which causes frequent state migrations. This issue becomes very significant in an edge-based cellular control plane. Frequent control handover causes frequent state migration, which affects the application performance. The third challenge is slow control plane state updates due to the slow message serialization engine ASN1. If we replace ASN1 with the faster serialization engine, our experiment shows that control plane updates can be speed up, and this in turn can significantly improve the application performance. Now, before going into detail of our solutions, I will present Neutrino's system overview in contrast to the existing deployments. In existing deployments, either the base station or a front-end load balancer perform the control plane load balancing. In contrast, Neutrino uses control traffic aggregator, which performs control plane load balancing and also implements a part of the state consistency protocol. Control plane function serves the user requests and also perform user state replication and the procedure completion. Now I will present how Neutrino solves all the 3 challenges. Neutrino solves the user state inconsistency issue with the state consistency protocol. The high-level goals of the state consistency protocols are: it should provide read-your-write guarantees for the user state, it should be able to recover quickly from the failure, and its failure-free overhead should be as minimal as possible. To handle the control plane failure, we are using a multi-level fault recovery protocol. We checkpoint the user state on procedure completion. To keep its overhead minimal, we are doing it asynchronously, but it does not ensure consistency. We log every controlled message in the volatile memory during a procedure execution, and if a control plane failure happened during a procedure, we replace stored messages on the backup replica to make it up to date. Since we are not keeping messages log for indefinite time, still there is a possibility that all the replicas are outdated. In case all the replicas are outdated or a CTA failed, we ask the user device to reattach to create fresh state on another control plane function. The second challenge was frequent control plane handover, which causes state migration on every region change. As a result, application faces long delays. Our solution for this problem is to proactively replicate user state in a wide area to reduce online delays in the data path. To handle the issue of frequent control plane handover, we have designed a proactive geo-aware user state replication scheme. This figure shows how geo-aware state replication is implemented with multiple consistent hash rings. Here ring 1 represents all the edge control plane function, and ring 2 also contains all the neighboring control plane functions in a wider region. A user device sends state updates to the local CTA. CTA forwards message to the primary control plane function on ring 1, and when a control procedure completes at the primary, user state is also replicated on the ring 2. The reason for replicating user state in the neighboring region is that on mobility, the user may find up-to-date state already replicated at the user's new location. The third challenge is the slow control plane state updates, and our solution in this case is a faster serialization engine. The existing serialization scheme ASN1 is slow. We evaluated different recent serialization schemes and introduced a faster serialization engine for cellular control messages. We also performed some cellular specific optimizations in the faster serialization engine to make it suitable for the cellular control messages. Now I will talk how Neutrino maintains consistency under different failure scenarios. In this sample scenario, we have two control plane functions, the primary and the backup. On user mobility to another base station, the user state is updated at the primary. The primary replicates state on the replica on procedure completion, and if primary fails after the state replication, the backup can serve as a primary as it is having up-to-date user state. Similar to the last scenario, if the user state is updated at the primary and primary fails before state replication on the backup, we replay log messages at the CTA on the backup to make it up to date. After the backup can serve as a primary as it is having up-to-date user state. In this example scenario, all the backup replicas are out of sync, which is possible due to the multiple control plane function failures or network partitioning. If the primary fails, in this case, an up-to-date user state does not exist in the core network. The user reattaches to the network to create consistent user state in case all the control plane function fails or a CTA fails. Now I will talk about the key evaluation results. In terms of procedure completion time, Neutrino performed up to 3.4 times better as compared to the other recent state-of-the-art schemes. Here the source of improvement is a faster messages serialization engine. Neutrino reduces the control plane failure recovery time by a factor of 5.6, and the primary source of improvement in this case is the faster failure recovery due to the state consistency protocol. Neutrino speed up wide area roaming by a factor of up to 7, and here the source of improvement is the proactive geo-aware user state replication scheme. The improvements in procedure completion time is also translated into the application performance. With the Neutrino, the self-driving car simulation app performs up to 2.8 times better as compared to the existing deployments. In conclusion, we studied the problem of application performance degradation due to the delays introduced by the cellular control plane. Our goal was to re-architect the cellular control plane for applications that requires low latency and high reliability. We have designed a state consistency protocol to provide consistency and fast failure recovery. We have designed a proactive geo-aware user state replication scheme to handle the challenge of frequent control plane handovers. And we have designed a faster serialization engine to speed up the control plane state updates. We also demonstrate through the testbed experiments that Neutrino can significantly improve the application performance. Thank you for watching the presentations. Question, please.
I will kick it off. So In terms of updating or improving the cellular control plane or the core network, I think one of the big challenges that we always see is that these core networks are mostly implemented as closed source implementations, like Ericsson's or whoever's. And so we don't really know necessarily that from their perspective, the latency or whatever issue is coming from their particular implementation. So I'm curious, did you have some insight? Were you able to look into the core networks at all and understand, like, for instance, that their serialization is poor and they needed to improve it? What sort of insight do you had in their specific implementations?
Okay, so if I understand the question correctly, you are asking about is the serialization is an issue on their sides, like the Verizon and AT&T and other core networks?
Yeah, my question is basically the implementations that are out there are closed source. And I believe that this is going to significantly improve what you presented, will improve latency for sure. But we don't know how they're implementing it right now. Or do you have some insight in how they did implement it?
Okay, so the specification documents and the other recent research proposals uses some the serialization schemes, like the specification documents mentions that the ASN1 use a serialization scheme in 4G, 3G, and from 2G. And there are some reasons for it: backward compatibility and low bandwidth usage. But when like the network assumptions change, like in 2G, 3G, the bandwidth was a big issue, but in 5G we have more bandwidth. So and in 5G the application wants low latency. In the 3G, 4G, and even the 4G, 3G, and 2G mostly were designed for the voice communication, where the latency was not as much issue. So the network assumption changes change, and there are now recent faster schemes to update to speed of the control plane updates. So this was the opportunity. We thought that we should use it, and as improvements are possible, so we proposed a scheme for it.
Excellent. So I think I understand you're saying, like, it's the specification itself was not sort of, or it made it very clear the way they were doing serialization. So just in the last minute, little over a minute, last question is, in terms of replication, did you have any issues where you were thinking of the cellular network of having a lot of space to put all of these machines that you're going to replicate the core network onto, where actually in reality a lot of cellular networks may have this one centralized room where the whole cellular network is operating anyway, so there isn't really an opportunity for replication?
So in our case, we replicate the state on the, we serve the user from the local edge nodes, and we replicate it at the neighboring edge nodes. Like if we say that here is a small city is served by a small data center set up in the telco central office, and there is another city like the neighboring, which we call the neighboring region. There is another central office having the core network. So we serve the user from the local core network at the edge node, and replicate state in the neighboring.
So it's in the neighboring. Yeah. Okay, that makes a ton of sense.
Yeah. Thanks for the presentation. Okay, I have a question. So I didn't quite understand your consistent protocol. You said you not make the primary and backup consistent, but instead of caching the log on the CTA. Is my understanding correct? No, you should mute your microphone.
Sorry for that. So during a procedure execution, we log the messages in the volatile memory. We cache the messages. We are not storing it on the persistent memory.
Sorry, so you didn't store that in the persistent memory?
Sorry, I could not get your question. Can you
Okay,
please repeat?
I just want to clarify the protocol you are proposing in the paper is that you log the message, the state, at the CTA node instead of all the way propagate to the primary and the backup storage,
Okay.
right?
Okay, I got it. So let me clarify it. So in the cellular networks, the control updates are performed in terms of procedures, which consist of multiple messages, request reply messages. So during a procedure execution, we log the control messages at the CTA in the volatile memory. And when a procedure completes, we back up the complete state on the backup replica. And then we delete the temporary messages logs at the CTA. So the protocol works is during a procedure, messages logged at the CTA, and when the message, when the state is backed up on another replica, we delete the temporary messages log.
Okay, I think in CTA you only have memory, right? You do not have the persistent storage there, right? So what happens if? Yeah, what happens if CTA fails as well? You know, they could for these operations, they require really high, like a 5-9 or 6-9 reliability. So do you think this the protocol you have just proposed though reach the same level of availability?
Okay, so in our design, if a CTA fails, the user device reattaches to the network through another CTA. But let me clarify one thing, that the CTA holds two important state information in our design: the temporary messages logs, which are only required if a control plane function failure, and the MF of the control plane function. So the messages logged are only required when if control plane function failure happens. If the control plane function does not happens, the only information we have to back up on the CTA is the map of the all available consistent control plane functions. So the CTA state can be backed up, but in our current design, we do not back up the CTA state. We reattach the user through another CTA in case of the CTA fails.
So it's reached the same, I mean, availability or reliability reliability level as currently the primary backup database?
Sorry, if the CTA fails, if I understand the question correctly, if the CTA fails, there will be an availability issue. This is the question.
No, I mean, it's still in the states. I mean, the states should be, you know, for current protocol, you need to update the primary and propagate all the update to the backup replicas, and when they get the, I mean, be consistent, then the transition finished. But I think your protocol trying to have this eventual consistency, right? So actually, maybe you just propagate to the primary and without waiting for the update to reach the replica, you just retain the retain the transaction, finish the transaction. But the problem here is that if there's a failures, then it's because the state is not be consistent, it's not persistent, right? So when there's a failure, so in some cases you could lose the state. I just will try to see if there's any consideration on that, because current operation is a cellular operation. They require very high reliability on this. They want to like 5-9 or 6-9 on their data reliability.
Okay, the consistency protocol we have designed is read your write consistency. So the CTA ensures the read your write consistency. If the up-to-date state is not available on any control plane function, or even if it cannot be recovered with the messages log at the CTA, in that case, we ask the user device to reattach. So with the reattach, the consistent user state is recreated on another control plane function. So yes, there is our scheme increased availability, but it does not ensure that always availability. There may be some still cases that all the control plane functions are not available, or maybe due to the partition or any other issue. So we do not compromise on consistency, but like this is a limitation, the CAT theorem, that if we can only ensure consistency or availability. So we are ensuring consistency, and that in turn can hurt availability a little bit.